Hartree-Fock was 0, of course, because I am doing H minus E Hartree-Fock. So this is the matrix of H minus E Hartree-Fock. I hope you remember. And of course, an intermediate normalization. Then entire singles is just 0. This is also 0. This is the only blocks which is singles to singles, which has some value. If you diagonalize this, one of the roots will remain 0. This is the root for E correlation. If you remember, this is 1 CS equal to E correlation 1 CS. This is the two block. One is a Hartree-Fock block, one is a singles block. This is completely diagonal in the sense that this number is decoupled from the singles. So if I diagonalize this block, then one of the E correlation will remain 0. Which means Hartree-Fock energy is unchanged. Is it clear? For CIS, is it clear? And this is a content of the Brillouin theorem. I thought I had said this repeatedly, that the Hartree-Fock with Brillouin theorem, Hartree-Fock with Hamiltonian is 0. So this is the meaning of saying that the singles does not directly interact with the Hartree-Fock. So if I have only singles, nothing will happen. But if I have singles and doubles, then you have 0 here, which is the Hartree-Fock, H minus E Hartree-Fock. And then you have Hartree-Fock with singles. So I'm calling it 0, Hartree-Fock is 0 with singles. Then 0 with doubles. So let's say I'm doing CISD. Normally doubles is much larger than the singles. And then you have exactly the same thing, singles with 0, doubles with 0. And then you have a singles block, singles doubles block. Then you have doubles, singles block, and then there's a doubles block. Now you see this is 0, no doubt. This is 0, no doubt. But this block is non-zero. This block also survives. This survives, this survives, this survives. So this is not a completely block diagonal structure because this is 0, but this is coupling with doubles and doubles couples with singles and then everything gets married. So singles contribute through the interaction with doubles. Is it clear now?
Sir,
Yeah.
I mean, if we sandwich the Hamiltonian between singles and double, between singles and double, and if it is non-zero, then we will say that it mix.
Of course.
Okay.
That's the meaning of mixing.
Okay.
That's the meaning of mixing. Yeah.
Okay, sir. Then, sir, quadruples. If we sandwich quadruples and the Hartree-Fock ground state, if we sandwich these two, then also it is 0.
No, that also is 0. No question about it. So
then why it is sir, Raj?
Tell me.
Sir, then why it is written then quadruple excitation are more important than triplet and singlet? I mean, singlet and triplet also.
Wait. That's a completely different. I told you very clearly when I did CI that the correlation energy depends only on the doubles. If you remember,
yeah,
correlation energy is C, IJB or ABPQ, whatever. I don't know what I have removed. ABPQ maybe, doesn't matter. And then there is a matrix element between Hartree-Fock and doubles, which is basically anti-symmetrized elements like this. Okay, so you can see that this is just doubles, Hartree-Fock with double excitation. But the point is that these matrix elements themselves have to be evaluated from a bigger matrix. So if you do CI doubles or CI quadruples, let's say, then you have a 0, then you have 0 singles, you have 0 doubles, 0 triples, and so on, right? And 0 quadruples. And then similarly, all the other blocks will come. I hope you understand. I can write down the blocks 5 by 5 blocks. Okay. So the point that I'm trying to say now is the 4 by 4 block. Yeah, sorry. The point that I'm trying to say that this is 0, no doubt. This is 0. This is 0. Only this survives. But to evaluate the doubles, I require all others. So quadruples will first matter in the doubles. That's the first thing. Then when we say that a quadruple excitation A, B, C, D, P, Q, R, S, when I said that this is a product of the doubles, this is certainly because of the fact that the two particle excitations are important. I told you, because of Pauli principle and the Hamiltonian being two electron operators, and their products are also important to some extent. So these quadruples can take place because of two pair excitations. But this is an approximation in the context of CI. So that is the reason I said quadruples are important. Of course, if you just look at this as zero, then you will say quadruples are important. But how do you know quadruples are more important than singles and triples? That's a good question. Just from the CI, you cannot tell by looking at the structure of the matrix unless you actually do a CI calculation and then show that if you do CI doubles or CI singles doubles, CI singles doubles triples, CI singles doubles triples quadruples, if you do this calculation for a series of molecules, then you will see the most important configuration is doubles. After that is actually the quadruples. So we can delineate the effects, but that is a numerical calculation. At this point, we are only giving a physical approximation. This will be further vetted by the perturbation theory later and all the pair theories. But the physical approximation, which was first given by Sinanoglu, I told you Sinanoglu's name, that you have two electrons in, let's say, AB, another two electrons, CD, whatever. They may not be degenerate, but these two and these two, they get excited to the virtual orbitals. At the same time, the time is only a notional thing here, but leading to an effect of quadruples. But quadruples essentially means all four particles coming together. That chances are very small. But this can independently take place and their products is also significant. So that is the reason we are saying this. But of course, in the context of CI, it is not obvious. And that is the reason CI is often called a black box method. The physics is not clear. This is physics. But if you do calculations in CI, then you will see that compared to doubles, triples and quadruples are, the quadruples is most important after doubles. So the most important is doubles, then the quadruples. So of course, in the CI context, you cannot justify by just saying this matrix element is zero or non-zero. So your question is, Hartree-Fock to triples is zero, Hartree-Fock to singles is also zero, quadruples is also zero. So why am I telling after doubles you have to take quadruples, right? Is that your question?
Yes, sir. Why it is like important then triple and
yes. So this cannot be justified by CI. If you want to justify by CI, then this will be justified only if you do a numerical computations. That is, you do actual calculation, and probably in the next class we'll show the actual calculation. The people did the calculations and showed. But the reason right now I said was because of a physical effects. That physically quadruples can be pair excitation, whereas triples cannot be written like this. Triples can be written as a doubles into singles at the most. Doubles is good, but this is very, very small. For the same reason, because of Brillouin theorem, singles is also very small, so the entire effect drops down. Whereas quadruples, coefficient of the quadruples can be written in terms of product of the two doubles, each of which is important. And that is the reason the quadruples is very more important. Of course, it is less than doubles, but it is more important than singles, triples, and so on. So this is only a physical reason that I said. I did not show. From the CI matrix, you cannot argue and show.
Hello, sir.
Yes.
So from this thing, we can conclude that the singlet can affect the another coefficient, that is
singles. Right.
But contribution is zero, but the effect of singlet state can
don't confuse the singlet. I'm talking of singles.
Singlet.
Not singlet. I'm talking of singles means singly excited. First, let me correct it. And effect of singles is not zero. Effect of singles in correlation energy for CIS only is zero. Please try to understand. That too ground state correlation energy. Only for CIS it is 0. But as soon as you have CISD, there is an effect of singles. I told you why. Because there is a doubles, and there is a doubles is there, and then this doubles is affected by the singles. So there is a higher order change due to the doubles. So singles will affect the result. So it is not right to say the effect of singles is 0. Effect of singles is 0 only when you do CIS. When you do CISD, there is a small effect. So you will see if you do CID calculation, if you do CISD calculation, there is a slight change. In energy, this change is very, very small. On the other hand, what I'm saying, if you do CI doubles and CI doubles quadruples, this change is much more. So this is more significant. You understand? So there is a change even here. But it's a very small change. This is much more significant. This cannot be justified by just looking at the matrices. This will be justified in the context of CI by actual numerical calculation. One can show. But this was justified by physical effects. And I told you that this whole idea that the quadruples is roughly equal to doubles into doubles is a content of the couple cluster method. And that is when you will realize why couple cluster is superior. Because couple cluster will bring in this physics. CI is not able to bring in this physics. So I am not able to see this. I said this because of my prior knowledge. You understand? Otherwise, I have to wait for the numerical calculation. Numerical calculations will eventually show. Is it clear?
Yes.
Okay. All right. So I just wanted to tell you, CIS, no ground state correlation energy. No ground state. Of course, you can get other states, excited state. CI doubles is significant. CISD correlation energy is of course slightly better than CID. Because singles is improving the result. But CI doubles quadruples is even better. If you compare to CI doubles. So I hope you understand. Whenever I'm saying better, it means energy is lower. Or the way I have defined correlation energy is also lower. So it is going down. So this is where there would be a very interesting variation method for the linear, that you know that if this is the ground state energy, then if this is Hartree-Fock, where my correlation energy is 0, right? Then every CI I do, CIS will keep it here. I'm only talking of ground state. CIS will keep me here, but as soon as I do CI doubles, it will go down. CISD, I'm just giving a schematic curve. CISD will be minor changes. But if you do CI doubles quadruples, the change will be much more. So it's all going down, as you can see. I mean, this is, of course, not to the scale. Maybe it is closer to the scale, I think, I believe. And then it goes on. It is not to the scale only because this is very close to E0. So if I put the E0 somewhere here, then it is almost to the scale. And eventually, of course, if you do full CI, you will come here. I mean, if you take I told you large basis set and full CI, you will give exact result. Experimental result, but otherwise this is a number, is the exact number in that basis set is a full CI. That means if I have taken all configurations. Okay, but the physics of doubles to quadruples, jumping from here to here, is not there in CI. This will be later clear when you do couple cluster. But what I wanted to mention the other day, that this physics was introduced by Sinanoglu. I told you the name last class, in a much earlier paper. In a paper which predates couple cluster, in at least couple cluster in chemistry, sometime in the 1960s. whereas couple cluster came in 1966. So when that will be done, it will be done. But at this point, I'm just trying to tell that whenever we do linear variation, we add more configuration, energy is going down. That is very, very important. All will be greater than equal to epsilon 0, which is exact energy because of Rayleigh-Ritz variation principle. You know that. But it's important also to note that as I'm increasing the number of configurations, it gets better and not worse. I mean, why didn't CISD go up? It will not go. It will always go down. This is a very important theorem, and today I'm going to speak on that. So actually, it's a nice question that you asked, that it came to what I wanted to do, and this is often known, this is again known due to Mcdonald, and the theorem is called Mcdonald separation theorem. In the context of the CI, it is also known as the Hilleras, three gentlemen, Hilleras, Undheim, and Mcdonald theorem, which you call HUM. This theorem is valid for linear variation, not for every variation. Like Hartree-Fock, I have been repeatedly telling, Hartree-Fock is a nonlinear variation because you change the orbital. But here I'm changing only the coefficients which appear linearly. So this is valid for linear variation. Is it clear? So what I'm going to do is today discuss the Mcdonald separation theory in the context of CI, but I will put it more generally. So let me first write it more generally. So let's assume that I am doing a variation of a psi tilde, which is sum over m-dimensional subspace in a fixed basis, phi I. So there is a fixed basis phi I, which is 1 to m. So it's an m-dimensional basis. I vary psi tilde. What do you mean by vary? Vary with respect to the Ci tildes, mci tilde. And you know that the equation that you will get is an eigenvalue equation of the Hamiltonian in this basis. So phi I h, phi j, phi I h, phi j, cj tilde equal to ei ci tilde. That's the eigenvalue equation that you get. We have seen that for linear variation, this can be shown by varying psi tilde h psi tilde average value, keeping psi tilde normalized, or by method of projection. I hope you remember. I showed you also by method of projection that you will get the same equation. Just to refresh your memory, method of projection was the last thing that we did with the intermediate normalization, but I am not doing intermediate normalization here because it's just linear combination of function. Anyway, intermediate normalization is not a special thing. No new physics is introduced. It's just to make one coefficient 1. So if you see what I had told, that if I put this in the Schrodinger equation, 1 to m, so this is h psi, equal to ei or e tilde or ei tilde, or e tilde you can say, sum over ci tilde phi I. Then what you do is to project this with phi j. So you project this with a member of the basis function. So phi j h phi I ci, sorry, I did not sum. I didn't sum over j. Ci tilde, sum over I, this sum is there, equal to E tilde. Then if I do this, this gives you Cj tilde. Because phi j phi I is delta Ij, so you'll get Cj tilde. So this equation and this equation is identical, except that I and j has been interchanged. So don't worry about it. What is j I'm calling I here, what is I I'm calling j here, but that's a dummy variable in m-dimensional space. So I have a m by m matrix, I diagonalize. That is what we knew from the beginning, and we found that the method of projection gives you the same equation. What the Mcdonald's theorem did was actually to look at this as a function of the basis. If I increase the number of functions, what happens? First of all, let me tell you that when I do the Mcdonald's equation, I get, for this particular eigenvalue equation, I get m roots. So let me call these roots as em. The square bracket just tells you the number of bases that is used, and then I say E1 or E0. It depends on how you start your counting. It doesn't matter. To EM minus 1 in M basis. So I hope you understood. I get M number of roots, E0, E1 to EM minus 1 in an M basis. So those are my M roots. I get M roots. And the way I order them is that the E0M is the lowest, E1M is the next lowest, and so on. So these are basically excited state, this is the ground state. I hope it's clear. By the Rayleigh-Ritz variation principle, all this EI is greater than or equal to epsilon 0. That's the exact value. That is clear because I have a Rayleigh-Ritz variation principle. So all of these will be greater than or equal to epsilon 0. Because that is what I have learned, that any psi tilde would be always greater than or equal to epsilon 0. Is it okay? Can I proceed?
Yes.
Yes, good. So let me put you a graph. This is my epsilon 0. Let's say some schematic graph. This is E0M. This is E1M, and so on. And this is, let's say, E minus 1M. So that is what I got. In M basis, there are M roots. These are my M roots, and this is, of course, my so this is my exact function. Okay? What is interesting is a theorem by Mcdonald which says what happens to these roots compared to the other roots, other exact states. So, of course, I have got an epsilon 0 here. Where is my epsilon 1? Where is my epsilon 2? I hope you understand. What are these epsilon 0, epsilon 1? These are the exact functions. So, this is my psi exact I, epsilon I, psi exact I. These are my exact states, ith root, ith wave function, ith root. Again, I equal to 0 onwards. So compared to epsilon 0, of course, epsilon 1 will be higher. Question is, where is it? Is it here? Is it here? Is it here? I'm trying to arrange my M roots with the M exact states. I hope you understand what I'm trying to do. I know all of them are greater than epsilon 0, but I have no idea about any bound on the excited states. That was not possible. Remember, Rayleigh-Ritz variation principle only gave a ground on excited ground state, bound on the ground states. But what I'm now going to give is this Mcdonald's separation theorem, which is sometimes called interleaving theorem. Interleaves. Gives you a very good handle to look at bounds for the excited states in linear variation. I'm only talking about linear variation. Please remember now. So what this Mcdonald principle says, that between the two roots, what do you mean by roots? The roots are the roots of the eigenvalue equation. Between the two roots of an eigenvalue equation, So I have m roots, which I have written here, but I can take up any two roots. Between the two roots lies one and only one exact state. So all of them are epsilon 0. Now what I'm saying is that between E0 and E1 lies one root. I call that epsilon 1. Between E2 lies another root, epsilon 2, and so on. I'm not going to prove this theorem. The theorem proof is very complex, but you can believe me, this just directly comes from the eigenvalue equation. It's really a theorem on eigenvalue equation, how they are ordered and the bounds and the roots of the eigenvalue equation. But if this is so, then we have a very, very interesting theorem. You can see here that, of course, E0m is greater than or equal to epsilon 0. That is very clear. So this is my epsilon 0, this is greater. And of course, if this is greater than or equal to epsilon 0, all roots are greater than or equal to epsilon 0. But that is saying nothing. It is just restating the Rayleigh-Ritz principle. But because of the fact that between these two roots lies one root, now I can say that E1 is also greater than or equal to epsilon 1. I hope you understand what I'm saying now. Because the Mcdonald said between the two eigenvalues lies one root, one exact state, sorry. I'm calling these roots and these exact state. So that means E1 must be above epsilon 1. And similarly, the root E2 will be above epsilon 2 in an n-dimensional basis. And so on. So Em minus 1 in an m-dimensional, this is the mth root because I'm counting from 0. So don't get confused. Huh? Is greater than or equal to epsilon m minus 1. Again, I'm counting from 0. So this is my m minus 1. This is actually mth root. In an m, this is only m-dimensional basis. So because of this interleaving theorem, each of these roots are greater than equal to the corresponding exact states, exact energy. The only thing that I stated is this theorem, without proof, This is all that I needed to state. And Mcdonald actually proved this. This is called separation theorem, interleaving theorem, various names are there. But this is an amazing theorem which simply tells you that if I have m roots, each of them is an upper bound to the corresponding excited states or corresponding states, exactly. So each of the roots when I say roots, whenever I say roots, it is an approximate, it is solution to the eigenvalue. I've got m of them. He is an upper bound to the corresponding exact. So E0, epsilon 0, E1, epsilon 1, E2, epsilon 2. Of course, if E0 is greater than epsilon 0, all of them are greater than epsilon 1. All of these are greater than epsilon 0. All of these are greater than epsilon 1, and so on. But importantly, the E2 is greater than epsilon 2. Has to be greater than epsilon 0 and 1. Hence, because they are also ordered in the increasing order of energy. So that's a very, very important theorem. And this actually tells you, for the first time in a linear variation, I am obtaining a bound, which is upper bound, of course, to the ground as well as all excited. These are exact excited. Which is a direct result of the Mcdonald separation theorem. Now I will state something which is very important after this. Let's now do a variation using the same m-dimensional basis. Remember, this basis is exactly same. And then after this trial function, I add one more function, which is, let's say, Cm plus 1, phi m plus 1, tilde. So I'm now going to do a new variation where I don't know the coefficients. These coefficients are first obtained by eigenvalue equation, if you remember. So they are obtained from the eigenvalue equation. Now I have added a new function with a coefficient C. I have to do another variation theorem for everything. So now my problem is m plus 1 dimension. I hope you understand. I have increased the dimension of the problem. If I do linear variation, I will again get an eigenvalue equation, right? But in m plus 1 dimension. That is a very important part. So if it is m plus 1 dimension eigenvalue equation, I will now get m plus 1 roots. Because you know in eigenvalue equation, you get number of roots which is same as the number of dimension. Before that, you remember, I got m roots. M roots, E0. E is, whenever I'm writing exact states, I'm writing this italics E. Otherwise, it is this E. So these are the exact roots, the red ones. The black ones are my exact states. But now I will get m plus 1 roots, which means I will have E0 m plus 1. I will have E1 m plus 1. I have E2 m plus 1. Em m plus 1. I hope you understand. I got one extra root. So again, 0 to m counted, it is m plus 1. So I got one extra roots. But what is important, that the equation is now different, because the eigenvalue equation will be a Hamiltonian matrix in this m plus 1 dimension of the m phi I and phi m plus 1. And when I solve the equation, again, because of the coupling of this, all roots will change. Only for very special case like CIS, because of Brillouin theorem, it is perfectly block diagonal. If you add such a term which is completely decoupled with this m term, doesn't couple, then of course it will not change. But otherwise, in general, all the roots will change. Is it clear? So all these values will change. So this is not the same as E0 of m. So E0 of m that I wrote here is different from E0 of m plus 1. It is the first root, but E0 of m will be different from E0 of m plus 1. I hope it's clear. Because I have a new matrix. and there will be coupling. One, of course, you can say only one term is added in the matrix element, but that itself is sufficient to change all the roots in general. Okay, in general. So they will all be different. Now the question that I'm going to ask, how are they positioned with respect to the exact states? First of all, Rayleigh-Ridge variation principle always holds. That means they are all greater than or equal to epsilon 0. So they are all greater than or equal to epsilon 0. But what is important here is that when I look at E0 m plus 1, that will actually go down. So the root that I get for the ground state in a larger basis is actually less than the earlier value, yet because of the Rayleigh-Ridge principle, it will continue to be greater than epsilon 0. Then what is important is that this epsilon 1 will also be greater. So E1 with m plus 1 basis will also be lower than E1. But again, because of my interleaving theorem, this will be now greater than or equal to epsilon 1. Because the interleaving theorem will now work in the m plus 1 basis as well. So if you extrapolate this, each of the roots, EIM plus 1, will be less than or equal to the roots in the m basis. I equal to 0, 1 to m minus 1. But of course, in m plus 1 basis, there will be another root. That will be higher than all these roots, obviously. That's a larger root. So that will be higher in the EM m plus 1 basis. But the earlier roots, they will all go down. Yet, interleaving theorem will hold good, which means they will continue to be upper bound to their corresponding states. So that means now I will just draw a diagram with 3 states. So let's say my m equal to 3, and hence m plus 1 equal to 4. So I'm going to construct the 4 values. So this is my E0 in 3 bases. This is my E1 in 3 bases. This is my E2 in 3 bases. So that's all I get in 3 bases. And of course, the ground state, exact state is here. Due to the interleaving theorem, there will be one root here. There will be another root here. Of course, there will be another root somewhere, epsilon 3. I am not bothered because I can only bother about 3 roots. Now I do a calculation with 4 roots, 4 bases. So there's 3 bases and additional bases that I talked of. You don't change this basis, the same basis but additional basis. So I just did the same problem. What will now happen is that I will get E0, but this will now become E0 in 4 bases, which is lower than this. I will get E1, which is again lower than the previous E1, E1 4. But because of the interleaving theorem, in the 4 bases, there will be one state, exact state between these two. So this cannot cross. Because if it crosses, then what will happen? The exact states will never change, right? Exact states are always in the same position. But if it crosses, then the interleaving theorem will be violated. So they will not be able to cross. So similarly, E2 will become E2 of 4. And then, of course, a new root will come up, which is E3 of 4. And we know because of the interleaving theorem, there will be an epsilon 3 here. Between these two roots and 4 bases, there has to be another root. So this is again an upper bound to its corresponding epsilon 3. So please try to understand this diagram, what is happening. So this is a very interesting problem where I can now say that each of the epsilon I, and this is what I said, each of the epsilon I in m plus 1 basis is less than or equal to epsilon I in m basis for the mth root. And of course, there will be an additional EM m plus 1, which will be greater than or equal to epsilon m because of the interleaving theorem. But since the interleaving theorem works, although they will be less, they will go down, they will never cross epsilon 1. So let's say E1 m plus 1 is less than or equal to E1 of m. But both of these will be greater than or equal to epsilon 1. So epsilon 1 will always be the lowest. And of course, epsilon 0 will be also lowest. The lower roots will be anyway lower. So I can specifically say epsilon 1 would be less than or equal to E1 m plus 1, less than or equal to E1 m. And in general, I will say all EI is less than equal to EI m plus 1, less than equal to EI m. So this is a very powerful theorem, a powerful bound. So I have said quite a few things. One is that because of the interleaving method, each of them will be always greater than or equal to the upper bound, its exact states. Second thing that I told, if you increase the basis set, keeping the old basis and then adding a new basis, the result always goes down. Yet the exact states always becomes lower. So no root, there is no curve crossing. So the roots cannot cross the curve. So what will happen eventually, I will tell you, when you do E1, 4, etc., and you increase the number of bases, what will happen? These values will finally go down and asymptotically reach its exact limit. Asymptotically, as you increase the dimension, but never, it can never cross here. Because if it crosses, interleaving theorem will be violated. Because then there will be two roots which are not separated by one exact state. So each of these will be slowly converging to its exact state. And that is a very, very powerful theorem. I hope you are realizing that that's a very, very powerful theorem. And that is the reason we say that the CI is applicable to excited states. We'll understand why. Because I have a bounds for the excited states. More importantly, CI is improvable, which means if the basis is increased, each root goes down, and yet remains an upper bound. To the corresponding exact state. I hope you understand. And if that is so, it means it is improvable bound. Not only it is a bound, but as I'm adding more and more number, it is improving. Look at E03. The difference was this much with epsilon 0. Look at E04. The difference has gone down. So it has improved. If anything is going down, remaining upper bound, that means this value is actually improving. Every root, it is improvable. So not only you have an upper bound for excited states, you have an improvable upper bound. I hope you understand the meaning of improvable. I can improve it. Improvable upper bound for excited states. And this improvement is achieved by adding more basis function. How do you improve? By adding more and more function. Is this clear? So every root improves. That means it is going towards exact state by going down. You come from here, is going down. And yet, it never crosses. So you can do an E3, let's say 1000 basis. Doesn't matter. This will be always greater than epsilon 3. And more interestingly, what will happen to E2, I don't know whether it will cross or not, but it will never cross the epsilon 3. However large the basis is. So by small number of basis functions, 3 and 4, you can see what is happening, that these numbers are all going down. E2, 3 to E2, 4 going down, but it will never cross E1. E1, 3 will still be lower than E2, 4. Because at E1, 3, it cannot cross here. Because there is E2, which will be higher than E1, and there has to be an exact state between this. So this is a very general theorem. I will again come back tomorrow to explain this, but it's a very, very interesting theorem. And this now tells you, if you do energy CI doubles and energy CISD, same doubles with same singles, the energy of CISD will be always less than or equal to energy of CI doubles. Is it clear now from the Mcdonald's theorem? Because I already told that if you have m plus 1 basis, it improves, every root improves. It means every root becomes lower than the previous m dimension. So my m is now CI doubles. M plus 1 is CISD, just a symbolically I'm telling. But number is more here. So of course this result will be lower. But it will be bound to its one corresponding state. Whatever is the corresponding state. That I cannot number the exact states. That depends on what is the value of singles, doubles, etc. So this is a very, very interesting theorem. And of course, if you have a large number of states, you can very meaningfully apply this. The Hume theorem, and this is a very special property of linear variation. Very special property of linear variation. This kind of property is not there for other variations. If you increase the number of functions, energy going down, energy will go down, but of course the fact that it remains greater than its own corresponding exact states is not true. They will only have a Rayleigh-Ritz upper bound, which means they will be all greater than the ground state, exact state. But in the case of CI, all excited states have a bound. And this is not only for ground state, for every state it will improve. So this is for every state. So if I am writing this is true for every state. Not just for ground state. Every state energy of CISD will be less than or equal to energy of CI doubles. Because of this Hillera-Sondheim-Mcdonald theorem. So many times it is called Mcdonald separation theorem, many times it is called just Hume. So two important properties I have used it. One is this. What happens from m to m plus 1? And this is exactly what I have done here. And the second one is this, which is basically translated as this. Without proof, I've only used the theorem. And I just have given you interpretation. Of course, the proof of this theorem as well as this theorem can be done, but it is just mathematical. It's just a mathematics and nothing to do with quantum chemistry. It is the mathematics of the eigenvalue equation. Please believe me. Because as long as this is an eigenvalue equation, that's it. So it's a mathematics of eigenvalue equation from where you get this. And of course, you have, since it is Hamiltonian, they are relating to the exact states. So the quantum mechanics comes only to that extent. It's relation to the exact states. But obviously, this part is simply mathematics. So I am not attempting to prove, but those who are interested can read the Mcdonald's paper. I think it was in 1933, the first Mcdonald's paper. If I remember right, it was the 1933 Physical Review where it came. So those who are interested can read the Mcdonald separation theorem. Is very, very fascinating. And of course, later on, Mcdonald proves that if you improve the basis set from m to m plus 1, how each root goes down, keeping the upper bound nature to the corresponding states, corresponding exact states. Are there any questions? I will close here today. So I think that also explains this that I was telling from CI double, CISD, and they'll all go down. And eventually, of course, full CI. Full CI is the best for every blah, blah, blah.
Sir?
Yes, and full CI will actually become its corresponding exact state because it has got everything. That's why we always write greater than equal to. So it's possible to become equal. Yes, ask.
Sir, so apart from like CI method, is there any method where interleaving theorem might not hold, like where linear variation is not done?
No, I'm not understanding. CI is a linear variation.
Uh-huh.
So interleaving theorem is for linear variation. Now, what is your question?
So apart from CI, is there any other methods where interleaving theorem fails? I mean,
No, you're asking a wrong question. In CI, it does not fail.
no, in CI it doesn't.
Yeah, so you are saying, of course, all other methods, there is no interleaving theorem. So let's say Hartree-Fock variation. So wherever there is a linear variation, only there is interleaving theorem. And CI is linear variation. So why should why should the linear interleaving theorem be there in other cases? This is a result of a matrix eigenvalue equation. So of course, only for CI there is interleaving theorem, and that's a case of a linear variation. You understand?
Yeah, got it.
So if I have just 1 minute. Hello, I'm joining in 2 minutes. Hello, I'm joining in 2 minutes. Huh? So yes, of course, if you have variation theorem of all kinds, there will be no interleaving theorem, only for linear variation, and CI is a linear variation. So CI is very special, but CI has this beautiful thing, upper bound excited state. CI has a bad thing. So I told you that if you do CI doubles, it cannot dissociate H4. Today I could not review that. You remember? H4 does not go to H2 plus H2, right? I had to do CI doubles quadruples, full CI. So this is called the size consistency or dissociation problem. And one of the problems with CI doubles, I told you that it is proportional to square root n. You remember when I wrote for dimer, it was coming square root 2 in the middle, that E correlation formula. So that is a problem. I'll come back to this. So CI is good. Simple matrix eigenvalue equation, good because it gives you all excited state bounds. Bad because in a truncated CI, I lose chemistry. So what do? And that's the problem. There are very few approximate methods which everything is good. So we will see the next approximate methods, perturbation theory. There are a lot of good things. But again we have to converge in orders of perturbation, which is sometimes very, very slow. And that is where we will try to place you the couple cluster, where most of the things are very good. Okay, and some other methods. I think there will be some pair methods, such few other things we'll do. We'll see how much time we get. Is Sangita there right now? Can I come out of the presentation first? Well, Sangita is not there, so but I will continue to take the class tomorrow. With a little bit this thing, I'll wind up the CI, entire review, and wind up the CI, and then probably from Friday or Monday, I will ask her. She will start another part of introducing to you second quantization. Second quantization is a very important part, and then eventually I will again come back for perturbation theory. That's how we have divided, and then Sangita Sen will come back for finishing with couple cluster. So just so that we have some share, and that's how we'll complete it. Okay. All right. So yeah, I have to go to another meeting. So I hope if there is still any question, I can take it up. Otherwise, tomorrow at 3 o'clock. Right? Tomorrow is at 9 o'clock. Is that right?
Yes, 9 o'clock.
Yeah. So I will tell Sangita, since you have taken this class, is it possible that tomorrow's class we need not have? We can just directly go to Friday's class. Friday 3 o'clock or whatever. Because tomorrow I have a little problem. I didn't realize I have a meeting, and it will become very difficult for me to manage. Unless you give me some other time, evening or something.
Like tomorrow evening?
Yeah.
It's fine with me, sir, but I don't know about others.
Yeah, I don't know others can opine. Says tomorrow's like.
We may discuss in group.
Yeah, 6 o'clock. If you can do, quickly tell me today. Otherwise, tomorrow we'll have to give off. We'll see. I just need one more brief class, even half an hour to finish up CI. Wind up, and then Sangita Sen will take. Okay, for the second quantization. So if you can give me half an hour. Tomorrow morning, unfortunately, we have some meetings, of Finance Committee and Board of Governors. So I'll be quite tied up. Okay. So either tomorrow evening or, yeah, Friday, of course, standard normal class is there. So please discuss in the group and then come back. Huh? Okay. Okay, thank you. I'm leaving now. Okay.